name's Helen Cullington. I'm a clinical scientist at the University of Southampton. I'm going to be talking about cochlear implant tuning, what, how and why. There's some references here that you may want to have a look at to give you some more background information about tuning. So have a look at these, but I'm going to give you the basics today. So when you talk about cochlear implant tuning, if you look in the literature, some different terminology is used. So depending what country, what clinic is talking about tuning, people call it mapping, programming, tuning, fitting. Sometimes it's called stimulation, initial stimulation for the first tuning session. So just to let you know that those mean the same thing, and I'm going to call it tuning, but other centres may use another term. And the main terms you see in tuning are T level and M level or C level. I'm going to explain what those mean. So this, of course, you're familiar with, a diagram of the ear showing a cochlear implant in place. So you can see the electrode curling into the cochlea, the implant package just inserted in the mastoid bone behind the ear. So the part that tuning is responsible for is turning the signals into electrical energy and sending this electrical energy to the electrodes inside the cochlea. So that's the part I'm going to talk about today, and I think you'll have other lectures which will cover some of the other areas. So what are the aims of tuning? What do we want to do when we're tuning? Well, the aims are to make the new sound that the person is receiving comfortable, give them speech intelligibility, and also wearability. So what this means is setting the options for individual patients, perhaps in terms of volume control, sensitivity, telecoil settings, allowing them to wear and make maximum use of their sound processor. Why do we want to do tuning? Well, a cochlear implant sound processor has to be individually fitted to each person to make sure the electrical stimulation is safe and effective. It needs to be adjusted quite often at the beginning as the implant system, the electrode array, and the patient adapt to the new stimulation. So why are patient maps so different? Why can't we just set an average map for everybody? Well, of course, although the device may be the same, the anatomy is going to be very different in different patients. So there may be very varying numbers of spiral ganglion cells. There may be a varying distance between the electrode contacts and the ganglion cells. Inside the cochlea, the fluid and the tissue density is going to be different in each patient. And of course, all people who receive a cochlear implant have a different experience and history of sound. So what I mean by that is some people may have been deaf for 30 or 40 years before they receive their implant, some people perhaps just for a month or two. So of course this is going to affect how the patient perceives sound. So what do we do in tuning? Well, the goal is quite simple. What we're trying to do is convert the acoustic input, so the sound information, to electrical sensations, so pulses of electricity that are between the just audible level, so where the patient can just hear the sounds, and the maximum comfortable level. And the two main things we often work on setting are the T level, or the threshold for electrical stimulation, and the C level, sometimes called the M level. So C level refers to comfort level, M level can refer to most comfortable listening level. So a cochlear implant's job is to convert sound, acoustic vibrations, into electrical stimuli. So the processor microphone is taking in a very wide signal. So the acoustic signal, if you think about everyday life, ranging from the tiniest little whisper up to a jet aeroplane taking off, it's a very wide dynamic range of sound that the microphone is taking in. And this needs to be converted into electrical signals. One problem is the dynamic range for electrical signals is much, much smaller than the acoustic dynamic range. So the acoustic range, perhaps from 0 to 120 dB, has now got to be compressed into a much smaller electrical stimulation range. So this diagram here shows incoming sounds, a large acoustic dynamic range, which somehow has to be compressed into quite a small electrical dynamic range. So this is some of the work that the sound processor is doing. If you think about a normal cochlea and what we're trying to emulate, so in a normal cochlea, there's perhaps 1,000 inner hair cells transmitting the information from the basilar membrane to around 30,000 auditory neurons. And then, of course, this information is being sent to a normal, usually, central nervous system. In an implanted ear, things are very different. So you have between 1 and 22, usually, electrodes within the cochlea. These are activating a much reduced number of auditory neurons, and then these are sending information to the central auditory pathways, which may well not be normal, perhaps due to auditory deprivation. So the cochlear implant has quite a tough job to do, and you can see from this is why a cochlear implant does not sound like normal hearing, unfortunately. We're really approximating what normal hearing does. So the main things that we want to map or tune are loudness and pitch. So looking how those are represented in a cochlear implant. So loudness, the stimulus parameter in tuning that's responsible for this is electrical charge. And many of you might know that considering this pulse of electricity here, the amplitude or the height of the pulse is this parameter here. The duration or the width of the pulse is here. And electrical charge is the product of these two things. So the amplitude times by the pulse width. So charge in microcoulombs is the current in microamps multiplied by the duration in microseconds. So what this means is that when you present a pulse of electricity like this to somebody using a cochlear implant, if you wanted to make the sensation louder for the patient, there's two things you can do. You can either increase the amplitude, so you can make the pulse bigger, or you can increase the pulse width, make the pulse wider, and both those things will increase the loudness that the patient perceives. And in the tuning software, it varies from company to company. Sometimes those things are increased in parallel, sometimes one is increased, sometimes the other. So the T level that you will hear a lot about, the threshold level, this is usually set as the lowest stimulus level where a response always occurs. So a 100% threshold, which is different, of course, from an audiometric threshold, where you're normally finding the 50% threshold. So what you want to do is send a pulse of electricity to each electrode individually in the cochlea and find out what is the smallest amount of electricity where the patient can definitely hear that information. So this is setting the T level on all the intracochlear electrodes. Now, in recent years, some manufacturers don't require the threshold levels to be set in all cases. So you will see in the software that sometimes the thresholds are automatically set at 5% of the maximum comfortable level, or sometimes 10%. And this depends on the processing strategy that's used. So next, the louder level, so the comfort level or the maximum comfortable level, it's C or M level. What this is the highest stimulus intensity that you can present to an electrode without causing discomfort. So basically for this, you stimulate all electrodes individually, usually, and you increase the electrical stimulation, so either increase the amplitude or increase the width until the patient reports that it's loud but not uncomfortably loud. And then this is done across the whole electrode array. And if the patient has judged their M levels or C levels correctly, then in theory, they won't ever hear an uncomfortably loud sound. So all sounds that are picked up by the microphone will be mapped between the threshold and between the maximum comfortable level. So any sounds that are too loud will be the maximum, only presented at the maximum level, the comfort level. Now, if an adult is setting their M level, usually it's reasonably straightforward to ask them to increase the level until it's loud but not uncomfortable. Sometimes we use visual scales where patients can see the information presented on a scale, sometimes pictures. But of course with children this is much harder to do, and we rely very carefully on observation of the child or baby and also objective measures, and I think you'll be learning about those in another lecture. So the other thing we want to map is pitch. So as you probably know, the cochlea is tonotopically organised, so meaning that different areas of the cochlea are responsible for different pitches of sound. So the entrance of the cochlea here is responsible for high-pitched sounds, going all the way down to the low-pitched sounds at the bottom of the cochlea. So the cochlear implant electrode takes advantage of this tonotopic organisation, and high-pitched sounds are sent to the electrodes near the entrance of the cochlea. Low-pitched sounds are sent deeper into the electrode array. Unfortunately, it's really hard for some patients to do any kind of pitch matching, and there's no guarantee that the pitch that you're sending to a particular electrode corresponds to the correct region in the cochlea. In fact, it's probably quite unlikely that it does. And there's lots of other things really that can affect pitch perception. So, of course, depending how far you insert the electrode, if there's any kinks or bends in the electrode array, the neural survival, so how the spiral ganglion cells are. Sometimes you can see a tip rollover, meaning that the tip of the electrode gets caught during surgery. It rolls over, so it bends back on itself. So of course then that is going to cause a different pitch perception. And that's something we would want to know about, which is why we study the X-ray so carefully. Other parameters that we want to set in tuning, we want to eliminate any electrodes that are causing an uncomfortable sensation. So the cochlear implant usually has up to 22 electrodes, and that allows for some redundancy. What this means is if any electrodes are not giving a good sound sensation, or they're causing pain, sometimes they can cause a facial twitch or an eye pitch, sometimes even a vestibular or a balance response, then we would want to not stimulate on those electrodes. So really we want to pick the electrodes that are giving a good sound response, and we would want to eliminate any that aren't giving a good response. We don't want to waste any information by sending it to an electrode that it is not a good electrode for whatever reason. We might also want to set the input dynamic range. So you'll remember I said that with people with normal hearing, you hear sounds from perhaps 0 to 120 decibels, a massive acoustic dynamic range. But really with a sound processor, we may want to limit that a little bit. And a lot of the sound processing strategies will vary that acoustic input dynamic range adaptively to try and find and follow speech. We may also want to set the compression between the acoustic and electrical amplitudes. This can be varied, power requirements, and different sound processor functions. So for example, volume, sensitivity, telecoil settings. These are all things that are set during tuning. Something that the cochlear implant companies have given us in recent years is access to data logging. So what this means is by connecting the sound processor to the computer during a tuning session, we can access information about how long the patient has been wearing the sound processor. So here you can see it's a historical view here of how much the patient's been wearing the processor, increasing over time. They've been on air on average for 12.5 hours. So if this was a child, we might assume that's all their waking hours. It also very usefully tells you how many coil offs you're getting. So basically how many times the coil has fallen off. And you can also analyse the scenes that the patient is in. So this middle chart here shows you that this patient has been in a speech environment, the green, for just over 2 hours, speech in noise for 5 hours, quiet for 2.5 hours. And this can be a really useful counselling tool with patients and parents in order to show them what sort of listening environments they're in and what they can do to improve their perception. So what we also get in the data logging is the program usage. So most sound processors have the ability to set several different programs, and you can see from the data logging which one the patient has been using the most, any that they haven't been using. And again, this is a very useful counselling tool. So this is usually done right at the beginning of the mapping session, sharing this information with the patient or the parent to enable them to improve their access to sound. Now, in recent years, there's been some moves for self-mapping for patients. So a lot of patients with implants have told us that they want more control of their hearing. When they come to the Cochlear Implant Centre, it's a soundproof environment, and it's usually a quiet one-to-one situation. And then as soon as they leave the clinic, back to their normal life, it may be that it's very noisy, they have quite varied listening requirements. So some of the companies have looked into self-mapping, and I'm going to show you, you can link to a video about what patients think about this in the supporting material. And what you can see here is a remote control, and this has got the self-mapping enabled on it. So the patients can use this remote assistant fitting to adjust their perception of sound, adjust the balance, the tilt from highs to lows, wherever they want in their own environment. There's a couple of references here talking about self-mapping, which you may want to have a look at in your own time. So what I've got here is some typical maps from different cochlear implant manufacturers showing the parameters I've talked about. So on this map here, you can see the electrode numbers across the top, 22 down to 1. And there's a lot of information on this screen, so don't worry about all of it for the moment. The main things to look at, and this is what's common to all the softwares, are the comfort levels, or the red bars across this chart, and the threshold levels, so the green bars. So, and these are the actual values for them are down here. We've also got the pulse width, so the width of the stimulation pulse here, and this is something that may be increased or decreased to suit the patient. Also, of course, there's lots of other information here. So the blue here is showing the neural response telemetry thresholds. So again, this is one of the objective measures that you'll learn about in another presentation, but it shows here how they can be incorporated into the mapping screen to give more information. So some software from a different manufacturer here, and just something to note is that the order of the electrodes is reversed here, so these are 1 to 16, so always just keep an eye on that. And in this software, the comfort levels, or the M levels, are set here, and the threshold levels are set at a fixed value. As I said, some of the companies use this. Some other parameters you can see on the screen here. So talking about usability settings, you can see here that the volume range. So how much would you like the patient to be able to adjust the volume on their own sound processor? And this may be a child's program. This is set from 0 to 0. So whatever they do to the volume control won't make any difference. sensitivity parameters. This is the input dynamic range that I was talking about that you may want to change. Other parameters, of course, people with sound processors often want to use it with a telecoil, or use it with direct input, or with Bluetooth, with an iPad or a mobile device. And you can set during the tuning the mixing ratio, meaning how much they hear from the microphone and how much they hear from the external device. So this is some more information here in terms of processor function. So you can see here there's usually several different processing strategies to choose from, and lots and lots of parameters can be altered. So it takes quite a while really to learn the benefits of all these parameters when you first start doing tuning. Another company's software here. So again, a similar setup. The thresholds are at the bottom here, the comfort levels at the top. And what's interesting about this program is some of the electrodes have been turned off or deactivated for various reasons. So these two had high impedance, meaning that the electrical resistance of these two electrodes was too high. And it looks like the last one has been turned off because of a poor sound quality. So as I said before, if there are any electrodes that aren't giving an optimum response or are giving any kind of adverse sensations, we would want to switch them off and not send information to them. So another map here from a different manufacturer. So this time shifted around. So we've got electrode numbers on the y-axis here. So again, a similar look in a way. Threshold level, comfort level here. Some information about speech processing strategies. So you can see that although the different manufacturers, the software is laid out quite different, the underlying parameters are the same. So once you learn the principles, then usually you can find your way around the software once you've had training from the companies. Thank you very much for your attention today.